Okay, hello dear students and welcome back. Here we are in the course on environmental bioethics in the program, the Masters of Bioethics at St. Thomas University. And today we're going to be looking at natural cycles and human recycling. Right. To put it in context, we have been looking so far at basically the material composition of the Earth, beginning with the geosphere and how the Earth itself came about materially with that general process of inhomogeneous accretion. Then we looked at the gas component of Earth, the atmosphere, which serves the dual purpose of keeping organic life alive and also shielding us from meteorites and asteroids that would have destroyed the face of the Earth otherwise, and certainly life. Then we looked at the liquid component on the surface, on the crust, which is essentially water, salt water, fresh water. It's mostly salt water, as we know, and the various properties of water, physical and chemical properties, a little bit overall. We're going to pick some of that up today with the gyres of the oceans, okay? Specifically the Pacific gyre, the North Pacific gyre. Now we want to look at cycles, continuing with this kind of setting the stage for life, for the possibility of life. We see that matter is recycled on Earth, just like that law that states that essentially nothing material is created or destroyed. Everything is transformed. Since the Big Bang, the matter, at least the visible matter, the matter that we can measure on Earth, is in a dynamic state, really, is in constant transformation. When we look at these three spheres or layers of the Earth, the geosphere, the hydrosphere, and the atmosphere, it may look static in a short range, but in the long term, we know that it is dynamic indeed, it's flowing, it's moving, and it's typically a combination of these two forces of Coriolis and convection that make things flow around. By the way, the flow of the atmosphere and the hydrosphere, it's somewhat perpendicular to each other, because whereas the atmosphere flows generally vertically, right, by convection, heat rises and then it cools and it sinks, warms up along the surface of the Earth and rises again, and so forth. It's a general vertical cycling, skewed to the side because of Coriolis. In contrast to that, the hydrosphere, especially the oceanic gyres or currents, move horizontally. All right, they move horizontally, and part of that has to do with the fact that there are both fluids, gas and liquid or fluid, but whereas the gas takes up the whole of the space of the container, we can say that the container of the atmosphere on Earth is really a force, is gravity, right? It's what's contained in the atmosphere around the Earth. Liquid take up the bottom of the shape of the container, the lower part, and therefore the oceans take up the basin, what is known pretty much as the oceanic basin throughout the whole world. And that's why those two currents are in general perpendicular to each other, all right? And these are just natural laws of physics that are going on in the grand scale, in the scale at the whole Earth. We're going to focus now on these cycles of different elements and chemicals that are, again, vital for life, all right? Beginning with the water cycle, and then carbon, oxygen, nitrogen, and then other natural cycles in less detail, just to mention them. And in the second part of the lecture, we'll look at human recycling. Again, because we are the only species that actually produces garbage that is not recyclable naturally, all right? We produce an excess of trash because of the capacity to make things and to build things. And therefore, we are also in the process accumulating stuff, artificial stuff, artifacts that have been made up by humans now over decades and centuries and so forth. So we have to look at that too. Okay. All right, going forward then, let's start with we're going to look at water, carbon, oxygen, nitrogen, and then a few other elements in less detail. Beginning with water then, the water cycle is crucial for maintaining life precisely because we know that water is essential for life, right? And water on the surface of the earth goes back and forth between the two basic states of solid and liquid, and liquid and gas, and a little bit of solid, but that solid is mostly held either at the poles or at the mountain tops where there is snow or some glacier. And even that has a dynamic that is constantly melting on one edge and replenishing at another level. So we can start with the ocean, for example, and at the surface of the ocean, we have evaporation. So there are about 10 steps here, okay? Starting with evaporation, which is the transition of water molecules. This is just water, okay, H2O. Evaporates from the surface of the earth into the atmosphere, making that transition from liquid to gas. In other words, it receives enough energy from sunlight to warm up and to be able to break the surface tension. Remember, we talked about surface tension, all right? And so these molecules of water at the surface are constantly being dissociated from the liquid and incorporated into the gas form of the atmosphere, what we call humidity, essentially. And humidity is rising now that that water molecule, in your mind's eye, okay, a water molecule that goes from liquid to gas now will move, expand, or move out into lesser concentration, because now it's a gas and it's essentially trying to take up the space of the container, the atmosphere. But as it rises, it will cool and start condensing, and it will form then clouds, cloud formation. So that is water that is floating up there and it's being condensed. So little by little, these water molecules are now clustering together, and typically, excuse me, they cluster around some kind of dust particle, right? And as they start condensing, they become more and more dense, the water, and then that water will eventually drop as rain, and that is precipitation. So all these terms have to do with the flow of water. Of course, there is a transportation of the clouds, which typically follow the wind pattern, the general wind pattern, flowing from the ocean inland. Now, before we leave this beginning of the cycle here, I want to mention that essentially the water that evaporates from the oceans is just pure H2O. In other words, the salt mineral content doesn't come out, all right? It's as if we were to boil water in a pan or a pot in the stove, and we have added salt. We added salt to that water. If we continue to boil that water will evaporate, and what will remain inside the pot will be the salt that we added. So the salt does not come out of into the atmosphere. Some salt naturally does break loose. Let's say the ions do break loose, and so the breeze will blow it inland to the shoreline, and there will be, in Spanish we call it salitre. I forget what the term is in English, but basically there will be a thin spray of salt, but that's mostly along the coastline, and it's not too high above the atmosphere. Okay. But the point here is that the water that is evaporating from the oceans, from salt water, right, is essentially fresh water, just pure H2O. Okay, so the clouds blow in, and at some point they precipitate, meaning rain, and they can precipitate either on the flat terrain, let's say a plain or something like that, or they can precipitate on the mountainside. Now, there's also a phenomenon here on the mountainside, because when the wind is pushing against the mountainside and is going to move up the mountain range, what happens with that wind is it begins as, let's say, warm, humid wind, all right? Warm, humid wind pushes in, and now the mountain range pushes that wind upward. As the wind goes up, it cools down. So as it cools, there is precipitation. And by the time that wind current goes to the other side of the mountain range, it has lost its humidity. And on the other side of the mountain range, that wind will come down again. And as it comes down, it warms up, but it will be dry. And so you have this phenomenon, this natural phenomenon, that when you look at mountain ranges, you can see them essentially as combs, if you will, of humidity, combs of humidity. So that on the seaside side of the mountain range, it will be moist, there will be rain, precipitation, and it will be essentially green. There will be a lot of vegetation on that side, on the seaside part of the mountain. But on the other side of the mountain range, it will be dry, desertic, because then that air is now dry. That happens in the northern hemisphere, and the classical example is the Rocky Mountains. So that when we look at the Rocky Mountains, on the west side, it will be nice and green and fertile. And on the east side, you get the Great Plains, which is drier. All right, Colorado, for example. So let me see, Rocky Mountains. It acts like a huge comb. See if I can pull this up. Yeah, satellite imaging. Generally, you can see the pattern here, very visual. You know that these are satellite photographs, these are not paintings. You can see here how the west coast is green, and then it's dry on this side. That's the general pattern. However, that pattern in the southern hemisphere reverses. And look at this. Here we have the Andes, all right? Little tiny glacier there in Bolivia. And in the Andes, the pattern reverses. Why do you think it's happening here? Where's the wind coming from? The wind is coming from the east instead of the west, remember? So we have this, the wind pattern, because of the Coriolis effect, is blowing this way. And so the warm, moist air from the South Atlantic pushes inland, and this is fairly flat. This is a whole Amazon basin. Here it is, one of the largest rivers of the world, if not the largest, okay, or vast. This is the Amazon River. And so this is known as the Amazon Basin, and you can see how green it is just from satellite imaging. So that warm, moist air is flowing this way. It hits the Andes and it goes up, and as it does, it releases all that humidity, which then channels down, runs down into all these tributaries of the Amazon, making that basin very moist. But then on the other side of the Andes, what happens is that as the wind goes over the Andes range and comes down into the Pacific shoreline, then it has lost its humidity and it is very, very dry. In fact, this is a long strip of dry desert here. It's called the Atacama Desert. In general, this whole sliver, which is mostly Peru and Chile, you can see, all right? And so we have the opposite effect precisely because of the wind pattern. All right, so precipitation, and then depending on how high that mountain range is, some of that precipitation will be rain, but some of it will be snow, because then that water was so high that it crystallized, it was cold, and there will be deposition. And deposition with snow will accumulate on what is known as snow-capped mountains, and they will hold that snow up there. Some may compress into thicker and thicker snow, and with periodic melting and freezing, it may generate ice and even glaciers. But at the edge, at the lower edge, that water is melting, right? And it will start running down. So we have runoff, snow melt runoff or glacier runoff. Deposition also into the rock itself or into the soil, which will form underwater systems, aquifers. The aquifer flows underneath, all right? Also known as groundwater here, number 9, groundwater. So that is slowly trickling down through the rock, through the soil, where it finds a hard layer, and it will start running just by gravity further down, down, and eventually empty out into the ocean or into a lake. The lakes will also have the cycle of evaporation and replenishing. So that water, as it filters through, it also gets purified from impurities, bacteria, and so forth. But the minerals typically stay in solution, right? And so the water, the groundwater, which is typically used for human consumption, then in general, the lower the groundwater, the more pure it will be, the cleaner, but it will have generally mineral content. So for example, here locally or in South Florida, we have what is known as the Biscayne Aquifer, which is underground, all right? And there are various layers of the Biscayne Aquifer. And that's very clean water because it has gone through the porous rock of the sandstone, okay? And has acted as a natural filter for bacteria and other contaminants. But as it goes through that rock, it also dissolves some of it and it picks up a lot of minerals. So our groundwater naturally is known as, it's high in pH, it's basic in pH. It could be up to pH 9, 9.5, something like that. You know that 7 is neutral. So it's what we call basic water or hard water. Hard water, and if we were to get that kind of water through the tap naturally, then it's very difficult to wash things with it. It doesn't make suds, all right? It doesn't foam up. So typically the water treatment plants that we have, at least in Dade County, we're familiar with, they soften the water and they bring it down to a pH of about 8 or 8.5, something like that. So that it's more, it doesn't have as high mineral content. All right, one last thing I want to talk about here is a phenomenon that we might not be too familiar with in down in the subtropical region and the temperate region, but it does happen typically up in the mountains or even in the polar regions, which is called sublimation. All right, now sublimation is not univocous, it has several meanings. And I'm not talking about the psychological meaning of sublimation, but rather the physical-chemical meaning, which is this: when water passes directly from solid to gas, all right, from solid to gas, skipping the liquid phase, and that can happen with a combination of high altitude and sunshine. And I've seen this actually happen up in the Rockies, because my brother and sister-in-law used to live in Boulder, Colorado. And when I went to visit, periodically we would go camping, either summer or winter, into the Rockies. Just a beautiful country out there. And anyway, we can't actually see it, but what happens is over time, the snow, it becomes thinner and thinner and thinner, because the water molecules at the surface of the snow are going directly into gas state due to the high altitude and less atmospheric pressure. Okay, so remember, it's a combination, the gas laws, of either temperature or pressure, and they go in opposite direction. Higher temperature or lower pressure will cause whatever matter to change state from one state to another, solid, liquid, and gas. So sublimation is a phenomenon that happens typically up in the high mountain ranges or the poles, and also can happen on glaciers. There's another one here I forgot to mention, which is another type of water loss, that this one is directly related to plant material, to living plants, and it's called transpiration. You see it here. It's a little hard to see because of the white background of the mountains, gray background. Transpiration, okay? Now, transpiration is the water that plants lose through their leaves because of, it's kind of a necessary evil for the plants. The plants are always trying to conserve their water, but they do have to open typically the underside of the leaf a little bit to allow atmosphere to come into the tissue, the leaf tissue. Let me see a little leaf cross section here. It's an actual photo. So this is the top part of the leaf that is impermeable because it has a layer of cuticle that prevents it from losing water, essentially, kind of a waxy layer. But the bottom side of the leaf, all right, the under leaf, has these little holes, if you will, they're called stomata. And one stoma, several stomata. And what happens is that it allows some atmosphere to get into the tissue of the leaf, all right? And why is that needed? The mesophyll, or the middle tissue of the leaf. Why is air necessary inside the tissue? What happens within the leaf? Why is the leaf green? Photosynthesis, exactly, the process of photosynthesis. And photosynthesis begins with, well, actually, in the next slide, we'll look at photosynthesis. Photosynthesis needs a starting material, water, and CO2. The water for photosynthesis comes from the groundwater. So the roots are transporting water up the tree or up the plant, okay? So the water is in liquid form and it comes from the root system, from the ground. But the CO2 comes from the atmosphere, all right? And so some of the atmosphere needs to get into the mesophyll of the leaf, the inner tissue, so that the plant can use that CO2 to make the chemical reaction of photosynthesis and produce the glucose, the food that is needed for all of life on Earth, all right? And therefore, the air, the atmosphere needs to get in here. And as it does that, the water loses, the plant loses some water vapor through the hole, because the water, the plant is also respiring, okay? And in respiration, we give off water. It's the converse reaction of photosynthesis. We'll look at it in a little more detail, but just for now, I want to mention then that plants also lose water vapor to the atmosphere, and that is called transpiration, and here it is. We also transpire, by the way. Animals also transpire. We lose water through our tissue, through our skin, out to the atmosphere. Okay, okay, so this is the water cycle, and again, basic for life, as you can see, because at the end of the day, it's what's keeping the plants alive, and then the plants are keeping the animals alive, and so forth. All right, since I introduced the topic, let's look for a moment at this complementary reactions of photosynthesis and respiration, because this is pretty much at the biochemical level what is maintaining life on Earth, organically speaking. And it also involves the water cycle, again, at the biochemical level. So let's start with photosynthesis here. I mentioned that the starting products of photosynthesis, the starting materials, are water that comes, again, from the ground, normally, all right? And CO2 that comes from the atmosphere. So water in liquid phase and CO2 in gas phase. In a structure called the chloroplast, which is inside the leaf, and it has, it absorbs on the spectrum, on the light spectrum, it absorbs the various wavelengths except green in general. And so it reflects green, that's why it looks green, but it absorbs the other on the bluish side and on the reddish side. Those are the wavelengths that are being absorbed. And that energy then is transformed. There is an energy transformation from light energy to chemical energy, all right? And that transformation is the actual process of photosynthesis. It is a synthesis because the water and the CO2 are being synthesized into glucose, which is a carbohydrate. And remember, for carbohydrates, we need minimally carbon and hydrogen. There they are. And then as a byproduct of that reaction, as a byproduct, there is excess oxygen. And that oxygen is released to the atmosphere as just diatomic oxygen. Diatomic because the two atoms are together, it stabilizes them. And that is essentially the air, the oxygen that animals are using, and plants are also using that oxygen for respiration, because since plants are alive, they also respire, okay? They also respire. So this is the beginning of the cycle, which I'm using as an illustration for the carbon cycle at the chemical level. Carbon here forming the CO2 molecule, carbon dioxide. And then on the other side of photosynthesis, the product is glucose, carbohydrate. So you notice for every molecule, for every one molecule of glucose, how many molecules of CO2 are needed? What is the subscript of this carbon of CO2? How many carbons in CO2, in one molecule of CO2? One carbon, right? So when it's one, the subscript is one, it's not shown, just like in algebra. When it's one, it's not shown, it's a convention. So 6 carbon molecules CO2 molecules are needed to make one glucose molecule, okay? And this is, again, at the biochemical level, what we're calling sinking, carbon sinking, which is absorbing CO2 for the atmosphere. And that's why plants are so crucial for the whole issue of maintaining the proper amount of CO2 in the atmosphere. We'll see that at a bigger level, at the global level, in a few minutes, of the gigatons that plants absorb in the atmosphere of CO2, all right? So plants are playing a crucial role in maintaining the temperature of the atmosphere by sinking CO2 into organic molecules like glucose, and then also other more complex molecules are formed from the basic carbohydrate, typically cellulose. And cellulose then is actually literally stored in the tissue of the plant itself. All right, so this is sinking carbon. Then what happens is the oxygen, of course, is released into the atmosphere, and the glucose is typically eaten by herbivores. It's the first layer of the consumers, right? Consuming the food that the plants produce. Now we need to look at another structure in cells, in all living cells, that is the mitochondria. One mitochondrion, several mitochondria. So in the mitochondria, what happens is the complementary reaction, which is known as respiration. Again, at the biochemical level, what respiration does is it essentially oxidizes glucose, or it burns glucose, right, by using oxygen. And in that process, the chemical energy that was stored in the glucose molecule, right, as chemical potential energy, is now released, and that energy is used to recharge what we call ATPs, adenosine triphosphate, which is essentially the energy molecule of the cell. So metabolism uses, all the metabolic pathways use ATPs as a source of energy. You can think of them as little tiny molecular batteries that have energy stored in them for metabolism to occur. All the thousands of biochemical metabolic pathways are energized by the release of energy from ATPs. And so what happens is that mitochondria are constantly recharging these ATPs so that it can be used as an energy source in cellular metabolism. What I'm trying to say by all this is that any cell that is alive needs to metabolize by definition, and therefore needs mitochondria to be recharging those ATPs. And that also includes not only animal cells, but also plant cells. So plant tissue that is metabolizing needs to be alive, needs to consume some energy. So plants also undergo cellular respiration, follow? And that, because of that, they need to consume some of the glucose that they make, but they make an excess of glucose, so they have plenty stored to use up. And that storage typically is as a starch, which is a polymer of glucose. So what are the end products of cellular respiration then? Well, water and CO2. And again, for every glucose molecule that is burnt up, 6 CO2s are released, 6 carbon dioxides, all right? And molecules of water, also 6 molecules of water. Because see, you can follow the hydrogen, for example, 12 hydrogens in glucose, and only 2 in each molecule of water, so it will be 2 times 6 will make the 12. This water is water vapor, and typically we exhale that. So for example, when in our lungs, we exhale basically 2 gases, all right? Now we're familiar with the CO2 that we exhale, and that goes into the atmosphere, but also we exhale water vapor. And so if I do this with my glasses, okay, that fog that appears on the glass is humidity that is inside my lungs that I'm exhaling because of cellular respiration. And so we are also contributing, that's part of that transpiration here, all right, that water loss. So we're constantly losing water to the atmosphere, and that is also why it's important for us to drink water to remain hydrated, because it's a constant water loss through the process of cellular respiration. So this looks at the CO2 cycle, at the carbon cycle, essentially, at the molecular, at the biochemical level, all right? We need to expand it at a bigger picture. Well, all right, staying one more slide for the complementary reactions of photosynthesis and cellular respiration. You notice they're going in the opposite directions of the biochemical reaction here. And it's called a redox reaction because it's a reduction on one side and an oxidation on the other side. So the reduction is the photosynthesis. Carbon dioxide and water are reduced to glucose and oxygen. And then that's the reduction side. And the oxidation side is a reference to essentially burning, right? The glucose is burned with the oxygen in the opposite direction, generating CO2 and water vapor, okay? And it is that reaction that is able to recharge the ATPs. It also gives us heat, which, by the way, this is the heat that we as endotherms use in our body precisely to maintain the metabolism at a particular kind of a constant rate of 37 degrees centigrade or Celsius and about 98 degrees Fahrenheit. Okay? And what is holding that heat in our bodies, we who are warm bodies, mammals and birds, it's mostly because of the hair in mammals and the feathers in birds that we're able to maintain our, especially our core temperature, where most of our vital organs are located. All right, so there's a nice elegance about all this, starting with the biochemical level, all the way up to the tissues, organs, and the actual organ systems that are keeping the organism alive. And what is holding the energy, the potential energy, the chemical energy, and the glucose bond is precisely the carbon-carbon bond, which is known as a covalent bond, and it's a high energy bond. And when that carbon bond is broken, then that energy is released, trapped to recharge the ATPs. Okay, let's move forward now. Let's back out into nature again at the bigger picture and look at the carbon cycle within nature as a whole with organisms. Now, let's stick with the blue for now, which is the natural cycle. And then the red is extra. This is anthropogenic. Anthropogenic meaning that it's generated by humans, but also there is some of the, better to look at the red as the release of CO2 and the blue as the sinking of carbon. Okay, let's start with photosynthesis. That's where I left off in the previous slide. I said that this traps CO2, traps carbon from the atmosphere and sinks it into the ground, into plants. And also whether it's on land or marine with algae, and also the phytoplankton, which is a layer of microorganisms, of plant microorganisms that photosynthesize, and they are microscopic, and they start the food chain in the oceans, phytoplankton, which is eaten by the zooplankton. Typically algae, either they're single cell, some become colonial, but they're typically unicellular organisms. And you can think of it as a layer of microscopic invisible grass that is on top of the oceans on the first couple of feet, several feet of surface of the ocean. And that starts the food chain and the food web in the oceans, kind of parallel to what plants do on Earth. So all that is sinking carbon into, out of the atmosphere. Also, erosion sinks some carbon, and rainfall itself, because CO2 can dissolve in rain. In fact, when you have a lot of CO2 dissolving in rain, it makes rain acidic, right? And that's what is known as acid rain. That was a problem in Europe for a number of years, acid rain from excess industrial output of CO2. And what it was doing is it was essentially dissolving the ancient monuments that had been in many parts of Europe since the time of the Roman Empire, back about 2,000 years ago. Okay, and a lot of that is marble, which is kind of a basic stone. It's on the alkaline side. And with that acid rain, it was essentially dissolving. It was like pouring water on an aspirin. Okay, it was just dissolving it on an Alka-Seltzer. And so that was a big problem until they started regulating highly the output of CO2 in industrial cities and parts of Europe. Anyway, so we see carbon dioxide or carbon itself sinking into the oceans, sinking into the land, right, as sedimentation. Also, as the animals consume the plant, they are also integrating, we are integrating that carbon into tissue, carbohydrates that form our body. And a lot of that stays also in the skeletons and the other tissue that then gets sedimented into the soil, into the sediment layers. So all that is carbon sinking, right? It happens in the oceans, it happens on land also, equivalent, when animals eat the plants, herbivores eat plants, they are sinking carbon into their bodies, and then carnivores that eat the herbivores, they continue to accumulate that biomass, remember, at a 10-to-1 ratio. So that's all good CO2 trapping from the atmosphere into either land or ocean, mostly the sediment. Over a long period of time, that carbon also becomes the fossil fuels. It will eventually turn into first petroleum. And then if that keeps being compressed over a long period of time at high pressure, it will turn into coal. It's going from the liquid petroleum into solid coal, all right? And if we compress carbon even further, coal even further with tremendous pressure, a long period of time, eventually we get a crystal of carbon, which is known as a diamond, right? A diamond, which is a pure carbon crystal. All right. Also notice that animals and plants are also respiring, as I mentioned. So they are also releasing CO2. Some of that CO2 gets dissolved in the ocean water, and some of it goes out into the atmosphere, all right, also by evaporation. They should have added another little arrow here, a little red arrow, because plants, in addition to sinking carbon by photosynthesis, plants are also respiring, right? There should be another little red arrow here. And where else? Another one here also, little red arrow, because the plants are also respiring and producing CO2. Okay, but the main source then, okay, soil respiration, meaning that the decomposers, that's another element that I neglected to mention earlier. Remember the saprophytes in the big food web, the complex food web, the saprophytes are essential as decomposers of organic material, break it down into nutrients and minerals that the plants can then reuse and recycle. These decomposers are mainly what? Fungi and bacteria, right? As they do that, they're metabolizing because they're alive, and so they are also releasing respiration, they're also releasing CO2. So all that CO2 is coming out. In addition to the organic CO2, let's say, that is produced by nature by mostly respiration, there is also volcanic activity or geological activity that releases CO2 into the atmosphere. There is also fires, wildfires that are going on, and they release CO2 by combustion. It's just a fancy word for burning. And now this is mostly the anthropogenic factor, which is man-made. That's why we call it anthropogenic. Again, just another fancy word for man-made, human-made. You see, these structures are definitely artificial structures, a transportation or industry that is burning fossil fuels, and that is producing CO2 into the atmosphere. This little sector here, if you will, is extra, is added to the natural cycle of carbon. This is artificial. This is the concern with climate change and global warming and so forth. So we're going to look at that in the next slide and look at subbalance quantitatively. Before going there, I also want to mention that as CO2, as we pump more CO2 into the atmosphere and that CO2 gets dissolved into the water column of the oceans, it also acidifies the ocean. So that's another negative side effect, is acidifying the ocean, which will change the pH, and that is detrimental to the current life that is there, because the current life has been, the pH of the ocean has been fairly stable in a somewhat dynamic state, local regions, but generally stable, somewhat a little above neutral. And now the oceans are becoming acidified, and the most dramatic negative effect that we have of that is known as coral bleaching. And it's what happens with the corals is they expel the little algae that they have inside, called zooxanthellae. A little too much detail for now, but basically the coral themselves are transparent. What gives them the color is little algae that they have inside in a symbiotic relationship. And when the pH changes, they expel these algae from their tissue, and eventually they'll die. All right, and that's called coral bleaching. And all that's left is just the carbon skeleton, the calcium carbonate skeleton, which is white. So coral bleaching is generally a sign, a dramatic sign of ocean acidification, which is also in itself an indication that there's a greater amount of CO2 in the atmosphere, greater than normal. Okay, let's look at the balance. It's known as carbon balance. And at the annual, or carbon budget at the annual level, all right? And this is in gigatons. And so just to put it in content, a giga is a 10 to the 9 metric tons. This is measured again in the decimal system as a metric ton. And 1 metric ton is 1,000 kilos. So 1,000 kilos, all right? It's a metric ton. And 1 billion metric tons makes a gigaton. So that's the scale on which this is measured, these numbers. Again, let's follow the, let's start with the green numbers, which this is release. The green numbers is the release of gigatons of CO2 throughout the whole world in a year. So from microbial respiration, in other words, decomposition here, rotting, this is again fungi and bacteria. Globally, they produce about 60 gigatons of CO2 in a year throughout the world, throughout the whole world, all right? On the surface, on the land side. Plants, plant respiration, which we see, it's mostly vegetation on the surface of the earth, right? They also produce about another 60 gigatons of CO2. Whereas photosynthesis absorbs about 120 gigatons of CO2. So that's a balance there. Okay. You notice that photosynthesis absorbs globally about twice as much CO2 as plants are producing. Okay. And it also accounts for the CO2 that decomposers are producing, that saprophytes are producing. So let's say on land, there is a net balance of 0 because of the 60 plus 60 is being sunk by 120 gigatons of photosynthesis. Now, in the ocean, it's a similar dynamic. It's overall is considered about 90 gigatons of CO2 that are released from the surface of the ocean, about 90 gigatons, combine respiration and decomposition, all right? Now here's a phytoplankton. Notice how significant that phytoplankton is, of course, throughout the surface of the whole ocean, which is about 90%, right, of the surface of the earth. And that is going to sink about 90 gigatons. So there's a net balance there, of course. These numbers have the privilege of eons, of millennia, hundreds of thousands of years or millions of years that we've had life on Earth. And so there's a net balance there of 0. 90 gigatons are produced in respiration and decomposition of CO2. This is the carbon cycle. And 90 gigatons are absorbed through phytoplankton photosynthesis. Okay? Now, there's added, and the added is an added of 12, 3 from the atmosphere that is being produced from, sorry, start here. 9 is the fossil fuels. This is the estimate of gigatons of fossil fuel burning that is produced globally on an annual basis, 90 gigatons. Now, this splits up. Of this 9, 3 gigatons are absorbed by land photosynthesis, 2 gigatons are absorbed by ocean photosynthesis. So that's 5, right? 3 plus 2 is 5, minus 9 gives the 4 excess. So this is the challenge here. Since industrialization and use of fossil fuels for burning and for running industry, we have been accumulating slowly but surely 4 gigatons of CO2 in the atmosphere annually, all right? And this is the excess, and this is what could be causing the gradual increase in temperature. That other graph that we'll revisit later in this course, of the CO2 shooting up through the 400 ppm. Remember that we saw? Okay, so this is, at the end of the day, the big challenge right now. This 4 gigatons of excess of CO2 that we're accumulating in the Earth's atmosphere on an annual basis. That's the big challenge. Okay. Continuing then, let's look at another cycle now. This is the oxygen cycle. The oxygen cycle is a little more complicated because oxygen is kind of split up into 3 main molecules, if you will. 3 main molecules. Oxygen is either trapped in water or trapped in CO2 or just diatomic oxygen being in the atmosphere that is used for respiration. So let's stick with that one for now. Let's start with diatomic oxygen in the atmosphere, gas, obviously. You follow the arrows, respiration of animals, respiration of decomposers. All right. Down here, decomposers are also respiring. And there's also combustion that is that is using up oxygen. And then there is the combustion of fossil fuels. That all is using up oxygen. Now, release of oxygen, mostly from photosynthesis, right? If we follow, let's say oxygen, well, okay, oxygen trapped in the water molecule, then of course we follow the water cycle that we saw earlier through condensation that precipitates down into the liquid water that is either in the oceans or used by plants. And then photosynthesis will then release that oxygen as gas. So there's a transformation here, the oxygen going from liquid to gas from water to diatomic oxygen. There's also evaporation on the surface of lakes and ocean that makes up some of that, the water vapor in the atmosphere. The third type of oxygen is trapped in CO2. And again, it follows the cycle of respiration and photosynthesis back and forth. The CO2 then is also being recycled, but some of it is being sunk and so trapped in the crust of the earth. So bottom line, with oxygen, it depends if we're following just gas, diatomic oxygen, or if we're following oxygen that is trapped in the water molecule or oxygen that is trapped in the CO2 molecule. We'll follow somewhat different cycles. But either way, typically it goes through the complementary reactions of cellular respiration and photosynthesis back and forth. Sorry? Yes, okay. Weathering is just basically erosion of the rock, and there is oxygen that is trapped. There's diatomic oxygen that is trapped in the rock component, even down in the mantle area. In mantle, there is oxygen that is trapped there, okay? And that oxygen comes out when there is volcanic activity or other geologic activity, and that mantle is exposed on the crust. Of course, it's going to solidify and cool down. And then with weathering is mostly wind and rain, eroding rock. And when that rock becomes eroded, as we saw last lecture, it also releases oxygen, okay? Oxygen that is trapped there. So there is a gradual, slow but sure release of diatomic oxygen from the mantle to the atmosphere through the crust by the process of weathering. That's long-term, but it is real. Okay, excuse me for a moment because one of the students has sent an email. Okay, sorry. Let's go forward to the nitrogen cycle. It's another basic element necessary for life, of course, at the organic level, because nitrogen is very much part of proteins. Okay, our proteins are kind of the workhorses of metabolism, and they are essentially the ones that regulate, do all the body functioning. Now, proteins can be structural proteins or functional proteins, all right? They can be involved in the actual formation of tissues and organs, or they can be involved in metabolism itself. So briefly, the nitrogen cycle, this is at the biochemical level. We can start with diatomic oxygen, diatomic nitrogen in the atmosphere that is in gas form. We know it's about 3/4 of the Earth's atmosphere is diatomic nitrogen. We call it an inert gas. For example, it comes in and out of our lungs and it doesn't affect us. But that nitrogen is also fixated into the soil through the process of ammonia, which is a byproduct of metabolism, right? And ammonia is then deposited into the soil. bacteria break down that ammonia into nitrates. And the nitrates are being absorbed by plants for as a nutrient source. As plants process these nitrates and these nutrients, they will form proteins, for example, and vegetable proteins. For example, beans have a lot of proteins, right? And they're vegetable proteins. That will be a food source for animals. And also those proteins and then are incorporated into the tissue of the animals. Mm-hmm. But those proteins have to be broken down by the process of digestion. All right. So very briefly, in digestion, what happens is the proteins that we consume, that animals consume, either from plants as herbivores or from other animals as omnivores or carnivores, those proteins are broken down in our digestive system, mostly the stomach, because it needs a low pH, acidic, down to amino acids. And the amino acids are then absorbed through the intestines into the circulatory system, and then in our tissues, different tissues of the body, the proteins are reassembled into different types of proteins that are used for metabolism. So there's generally like 3 steps in the making of proteins, starting with the amino acids. There are 20 amino acids that occur in nature, and there are these medium-sized molecules, and typically amino acids have what is known as an amino group. In other words, there will be one atom of nitrogen involved in each amino acid. All right, like I say, there are 20 amino acids that occur naturally. Just to look at them briefly, some are hydrophilic, some are hydrophobic. And this is a little table of the 20 amino acids. Maybe this one is more complete, right? They all end, mostly end with INE. These are all the 20 amino acids, and they make up the basic unit of proteins. Amino acids are put together, assembled in a sequence, and this sequence is really what the DNA codes for, or the RNA. This is the sequence that it codes for, all right? So there's transcription and translation into a sequence of amino acids, which is called a polypeptide. And then polypeptides, these sequences, are folded 3-dimensionally in a particular way. They form mostly 2 different types of structures known as alpha helices and beta sheets. Too much detail, don't worry about that. But basically, they form these 3-dimensional structures, and polypeptides coming together form the actual primary protein. And then these proteins forming larger complexes form the actual functional protein, all right? And that functional protein is known as the quaternary structure. Let me see if I can expand this just a little bit. All right, so there are 4 stages, beginning with the, beginning with the amino acid. That's the primary structure. Then the protein, the polypeptide sequence, known as secondary. Then those sequences folding 3-dimensionally is known as the tertiary structure. This is still a single protein, all right? Single molecule. At this point, we're already into the thousands, hundreds of thousands of atoms, but a single molecule. And these coming together into complexes, which typically are duplications, form finally the quaternary structure, and the quaternary structure is the one that is functional in nature. This is one example. This one typically is the one that is used as hemoglobin that has 4 myoglobins. So each one of the 4 structures that make up hemoglobin is known as a myoglobin, and that would be the tertiary structure. And there are 4 of them coming together in a particular conformation, and at the center is an atom of what? Anybody know what is the atom in the center of a hemoglobin? Ferrum. It's known as a heme group, H-E-M-E, which is iron. So there would be an atom of iron at the center, holding together these 4 myoglobins, and that iron is what becomes oxidized, FeO2, and it is a transport mechanism from the lungs to the tissues of the cell. It's the transportation of oxygen from the lungs to the tissues for cellular respiration. So this is the transport agent, is the hemoglobin, which is the quaternary structure of made up of 4 complex 3-dimensional myoglobin molecules of protein. Anyway, that's just one example of the cycle. We back out from the biochemical to the bigger picture, the macroscopic picture of plants and animals, of nitrogen cycle, another one of the essential cycles in nature to maintain life. If, let's say, we begin with the decomposers here at the center of the diagram, the decomposers are breaking down organic material, including the proteins, right? They're breaking down into ammonium that then is further broken down into nitrates by bacteria mostly. This bacteria, they're called nitrophine bacteria. And these nitrates then are being absorbed by the plant as nutrients. And these nitrates, by the way, are dissolved in water. So there's a double purpose for liquid water in the soil. One is to be a water source for the plant, but simultaneously, because water is the universal solvent, right? The nitrates, the nutrients, and the phosphates, and all the other chemicals that the plant needs are dissolved in water, and so that gets transported into the plant. It's not just pure H2O, but the plant is absorbing. Follow? All right. There are also other bacteria that break down these nitrates and release nitrogen in the atomic form, gas form, into the atmosphere. Then that atomic nitrogen is also being trapped by other type of bacteria that absorb that atomic nitrogen directly from the atmosphere. They are found mostly in the roots of certain plants, and these are known as nitrogen fixing bacteria, and they are found mostly in legumes. And what is an example of legumes? The beans. Okay, and this is also a nitrogen source for plants, and that is why legumes typically are rich in proteins. Beans are rich in protein because of these nitrogen fixing bacteria. In addition to that, there's another little cycle going here with animals, as the animals, the primary consumers, remember, are herbivores. They're eating plant material, and part of that plant material includes proteins and other compounds that have a nitrogen base, right? In proteins, it's going to be all the way down to the amino acid level. So the animals will digest that protein and break it down into precisely ammonia and other byproducts that are then deposited on the soil, either as urine or defecation, or the actual animal that dies and will then be decomposed by the decomposer. And I say, thanks be to God for the decomposers in the world, fungi and bacteria. Otherwise, we would be covered literally in decomposed organic material from animals and plants, because plants also die at some point and decompose, right? Rot. So these decomposers are really spectacular, how they're keeping the whole cycle alive and processing all of these rotting material on the surface of the earth and the oceans also. Again, mostly fungi and bacteria. We don't see them. They're on the ground. They're microscopic, but they're definitely there in vast quantities. All right, so those are the three main cycles: oxygen, carbon, and nitrogen, from the biochemical level all the way out into nature. Now, there are a few other elements that compose the body. And so here's a little scale or percentage of these element composition of the human body. For example, most of our body is actually oxygen, but it's oxygen that is trapped in organic molecules, all right? Organic molecules, the carbohydrates, the lipids, the proteins, even DNA, it all has oxygen in those molecules, in those organic molecules. And the 18% or about 20%, about 1/5 of our bodies is carbon, 1/10 is hydrogen, 1/3 is nitrogen. So let's say it's more than 95% of our bodies is these four elements, just these four elements: nitrogen, hydrogen, carbon, and oxygen. And all the other elements are only 4%, okay? So less than 5% of our bodies are all the elements. Similar to the composition of the atmosphere, that we had those trace elements, and yet they are essential for life, including the actual CO2, which is one of those trace elements. So what do we have in this 4%? We have phosphorus, we have sulfur, calcium, potassium, sodium, chlorine, magnesium. See, all these are minerals that are necessary, essential minerals for life. And even down to trace elements, which are typically measured in parts per million. And they are iron, manganese, iodine, copper, chromium, cobalt, silicon, zinc, boron, right? All of these trace elements are also necessary for life, but they are in a minute quantity that is all regulated by our metabolism. And we typically get these precisely from nutrition, from the food that we eat, all right? So it's, you can see then there's going to be a phosphorus cycle, a sulfur cycle, and so forth. And all these essential minerals also are cycled back and forth in nature, mostly through our digestive system. Finally, there's one more that is left before we take a little break here, which is the hydrogen cycle. Now, the hydrogen cycle is, again, a little different because essentially one characteristic of hydrogen that makes it very dangerous. First of all, before we go there, hydrogen is what we call ubiquitous because it's really all over the place, but it's mostly trapped in organic molecules. In nature, it's trapped in organic or inorganic molecules, all right? We know there are two elements that are necessary for organic molecules. And here is a review of the 4 groups of organic molecules. They're also known as macromolecules because they're larger. Carbohydrates, proteins, nucleic acids, and lipids, all right? What's another word for lipids? Fats, oils, greases, waxes, all those are lipids. And nucleic acids, 2 types of nucleic acids, DNA and RNA, okay? Many different, thousands of different types of proteins, either structural or functional, and also carbohydrates, many different types, like cellulose, starch, and so forth. So again, it can be either structural or functional. Hydrogen is ubiquitous because it's found in all of these molecules. In fact, there are two necessary elements, minimally two necessary elements in all organic molecules, which is precisely carbon and hydrogen, all right? What hydrogen does, essentially, it covers the organic molecules so that it stabilizes them. So whenever there's for example, carbon that is a tetrahedron, carbon has four arms branching out, looking for bonding. Carbon tetrahedral structure. All right, tetra is a reference to four bonding possibilities. Typically, if carbon is not bonding to another carbon, for example, with a covalent bond, then it gets coated with hydrogens to stabilize it. All right, and so that's why hydrogen is really all over the place, but it's trapped in molecules. And again, thanks be to God for that, because hydrogen, as diatomic hydrogen, is highly flammable, extremely explosive, all right? And so in the atmosphere, it is estimated to be only 0.00005%, all right, percent. So if you want to turn this into a decimal, you would add 2 more zeros over here, all right? So 0.5 millionth of a part. You add 2 more zeros, you get 0.5 millionth of a part of diatomic hydrogen in the atmosphere. And that's really a good thing. Otherwise, our atmosphere would be highly explosive, as in the infamous case of the Hindenburg that went into flames, because hydrogen is also lighter. It's one of the lighter gases, and so it tends to rise. And in olden times, the balloons were filled with hydrogen until we realized that it was highly explosive. And so now, instead of hydrogen, what is used? Helium, which is the next element, the second element, all right, with 2 atoms on the nucleus instead of 1, 2 protons. And so helium is inert, it's not explosive as hydrogen is. And so that's a good transition there. But hydrogen is in the atmosphere, is mostly on Earth, is mostly trapped in organic molecules. And so that is a good thing. Okay, we've covered a lot of ground here in all these cycles. These are natural cycles, right? And 4 main ones are, just to review, water, and we have oxygen, carbon, nitrogen. Well, hydrogen is the 5th one, mostly trapped in these molecules, or the very tiny amount of diatomic hydrogen in the atmosphere. Those are the main elements needed, or atoms needed for life. Any kind of question or comment? All right, it's almost 11, so I think this is a good time to break. And then in the second part, we're going to be looking at human trash and recycling. So how do we go about this? Because as I've mentioned before, the animal species is the only one that produces excess garbage and trash beyond our own bodies decomposing, which is a natural process. And so we have to deal with that. Precisely the capacity for artifacts, and these artifacts sooner or later break down, and what happens? We just continue to accumulate stuff, garbage, artifacts on Earth. That is a concern, all right? Some of the material is recyclable, other material is much more difficult to recycle. So we're gonna stop here for 10 minutes more or less, or, okay, let's come back at quarter after 11 for the second part. No questions, no comments, then I'm going to pause. Okay, here we go into the second half. And we're now going to look at human trash and recycling, and the challenges and opportunities that we have ahead. First, we can divide human trash into various main groups, 5 main groups, right? Man-made trash, which are wood materials, wood-based, metal-based, glass, plastic, and electronic parts. And each one of these presents a challenge and an opportunity. The first 3 basically can be handled with recycling and make something useful out of them, so recycle. And that's why I'm introducing this topic here, kind of expanding on natural cycles, because again, we're the only species that produces extra stuff, artifacts, and how to deal with them. Wood is wood-based, paper, cardboard, fiberboard, all that can be recycled as long as it's relatively clean. So that is an opportunity for industry to make other artifacts which are then sold to at least offset the cost of the recycling. The same argument can be made with metal. Cars, trucks, planes, ships, there's metal everywhere, right? And that can be recycled too. Glass, as we know, in bottles, pane glass for windows, etc., all kinds of glassware. That can be recycled also, typically melting it and repurposing. Plastics is a challenge. Plastic comes mostly from petroleum, and it's harder to recycle because it lasts longer in nature. The polymers are more difficult to recycle, and it also spreads easily into nature, all right, because it floats around. And we'll look at some challenges here of the plastic and other waste that is going into the oceans. Finally, the electronic parts are also a big challenge. This is of more recent vintage, if you will, for humanity. In the past decades, probably, I would say half a century more or less. I remember when I was in my 20s studying biology at FIU, way before the priesthood, it was in the 1970s, the first computers were coming out. And FIU back then was a single building, Primera Casa PC, which is still there, kind of in the middle of the university. And the rest of it was just open field. Keep in mind that FIU, the main campus there on 8th Street, used to be an airport, an airfield, right? The old Tamayame Airport, which then moved further south, way down, I think 112th Street now, more or less, and the West Kendall region. So now it's the new Tamayame Airport. At any rate, that building had 5 stories, it still does, 5 stories, and the whole university was that building. Let's see, the first floor was, I think was the library. Second floor was the offices and administration and cafeteria. The third story was classrooms. The fourth story was labs. And the fifth story was the administration building. Half of the 5th floor was administration, including the president's office and all that. And the other half of the 5th story was a computer, one huge computer system that they had, the old UNIVAC things that looked like huge refrigerators, and they had this that went back and forth like this. And students, we would love to go up there because they kept that area like at 50 degrees Fahrenheit, something like that. It was really cold because those machines warmed up so much. You know, they heated up that they had to be kept at a very cold temperature. And so we would love to go up there to cool off from the heat. At any rate, those computers, our cell phones today probably have more power, more capacity than those huge computers that they had back then. And that was only, I mean, that's in my lifetime in 50 years or so. all right? So imagine in this half century, how much computer components and electronic components in general we have been producing because of this built-in obsolescence, right? Every few years, the machine is now obsolete and you have to get the updated version and so forth. So all this electronic trash is accumulating and accumulating. And this particular photo is from, where do we dump this? Okay, we dump it in other countries of the world. So we actually export garbage and we pay other countries to take our garbage. And there are these huge piles, mostly in African countries, where either there's no regulation or environmental regulation, or if there is environmental regulation, it's not followed because of corruption and so forth. And so literally there are these huge garbage mountains, hills, and people go in there and start pulling out electronic parts. And it's very dangerous because these electronic parts leak toxic chemicals and so forth, and that's all going into the ground, and they spend their lifetime pulling out these little electronic parts then to be sold in the market or something, or to be recycled. Precisely, they go after the copper and what other elements are there for recycling, but it's extremely dangerous and not healthy at all. All right, so this is a big concern now with recycling and repurposing electronic parts, which are accumulating, and it's mostly industrialized nations, North America, Europe, that is dumping on other parts of the world. Okay, so the challenge of recycling, all right, and how to deal with this. I want to start then and shift a little bit to the gyres and what is known as the Great Pacific Garbage Patch. At this point, we humans, this one species, has already dumped so much plastic into the oceans that is beginning to accumulate in these huge gyres. Remember the 5 gyres we talk about? North Pacific, North Atlantic, and then in the south, 3, South Pacific, South Atlantic, and the Indian Ocean gyre. Well, these giant gyres, these giant vortices, as they turn and churn, they are concentrating and accumulating the floating debris and the debris that is also in the water column, all right? And so there is now this garbage patch, which is not really a floating island of garbage, but rather it's in the water column itself. Some of it is toward the surface, and other particles, smaller fragments, are in the water column itself, which will get into the food chain and the food web, beginning with filter feeders as they start absorbing these microfibers. So now I have a series of little videos for you in the second part showing different aspects. First, I want to show this video of the garbage patch. And I had, okay, I was checking these videos yesterday, but I think I left the sheet in my computer at the home. Anyway, I have to, give me a second. Let me see. I have another sheet where I have all the links. I have all the links. So where do I want to go? I need to go into my OneDrive for a moment. Yes, here we go. Okay. Most of the links are here, but some I had to update. Sorry. Yeah. All right. It's becoming more cumbersome than from the actual slide. All right, let's see how the volume is.
Plastic pollution is one of the biggest threats the oceans face.
This one starts right away. Most of them are short videos. Oh, want to optimize for video here. Okay, so this one is explaining very briefly what is the known as the Great Pacific Garbage Patch.
Plastic pollution is one of the biggest threats the oceans face today. But how much do we really know about it? On its mission to solve this problem, the Ocean Cleanup just published the most advanced research ever on the Great Pacific Garbage Patch, the largest accumulation zone of ocean plastic on the planet. Scientists have been studying this area since the 1970s, mostly by dragging a small sampling net through the ocean. The Ocean's Cleanup's researchers believe this method was valid only for small debris and covered too small an area to reliably measure larger debris. So, in the summer of 2015, the Ocean Cleanup launched the Mega Expedition, crossing the patch with 30 boats simultaneously. In addition to using many small nets, 2 giant trawls were towed behind the fleet's mothership. In total, they brought back 1.2 million plastic samples. All were hand-counted, identified, and classified by type and size. A monumental task, taking a team of lab technicians 2 years to complete. However, the largest debris appeared less frequent and more scattered. Quantifying the debris required an area 20 times larger than the Mega Expedition to be covered, something only possible from the sky. The Ocean Cleanup ran the first ever aerial surveys of a garbage patch by converting a former military aircraft into a high-tech research platform. Cutting-edge sensors allowed them to reconstruct the 3D shapes of large debris to calculate their mass. The results of all this work? The Great Pacific Garbage Patch measures 1.6 million square kilometers. That is 3 times the size of France. The patch contains 1.8 trillion pieces of plastic, which equals 250 pieces for every human in the world. The total mass amounts to 80,000 tons, 4 to 16 times more than previous estimates. 92% of this mass is made up of the larger objects, all of which are destined to fragment into dangerous microplastics over the next few decades, if left under the effect of sun and waves. And because the findings show that pollution in the patch is increasing exponentially, the plastic is unlikely to go away by itself. These results paint a new picture of the problem and provide a baseline for the cleanup of the Great Pacific Garbage Patch, set to start in 2018.
Okay, so this is the first of these little videos explaining the problem and now some possible solutions. One example is the largest one is in the Pacific Ocean. It talked about these microplastics and microfibers, which is the breakdown little by little of that fourth component of trash here, the plastic component, which is very difficult to recycle in this massive amount, all right? So I want to, I don't know if you've heard about the microbeads and microfibers, but there are a couple of other little videos here that explain this. And one is longer than the other, but keep in mind that as plastic keeps breaking down mostly by ultraviolet and ultraviolet radiation from the sun, plus the ocean, the actual chemical composition of salt water continues to break down the plastic. You know how plastic over time starts getting brittle and so forth, all right? But the danger with that is that it actually becomes these microbeads and microfibers, which then get into the food chain at the level of the filter feeders. So here's a little one on the microplastics.
We finally found our dream home in the mountains.
It is bear country, though.
Hey, boo-boo, we hit the jackpot. Bear, look, corn on the cob.
Ooh, chicken. At least Geico makes bundling our home and car insurance easy.
T-bone.
For bundling made easy, go to geico.com.
It was completely legal. Dump plastic in the ocean until the 90s, and a lot of that plastic is still there because plastic lasts out there for a very long time. It just breaks down into smaller and smaller pieces. We know that over 300 species of wildlife have ingested this material. It's been reported in animals, and so as it is eaten by animals, it actually can move up the food web. And as the scientific literature on this issue increases, literally almost every habitat they've gone to, seamounts, Arctic ice, coral reefs, deep sea, it's become ubiquitous, and I don't think anybody would fight anyone on an argument that plastic debris has not become a contaminant of concern.
Collecting the samples by using a manta trawl. It's basically a big metal box with wings. It looks like a manta ray with a very long, about 12-foot mesh net off the back.
1, 2, 3, splash.
And at the end is a piece we can take off that has collected all of the solids. You rinse it all out, filter it through another strainer, and then put it into a jar. This has caught a lot of other stuff. If you want to take a look at what we're rinsing out of the screen, it's more tiny plastic.
What we're concerned about ultimately is what are the implications of trash going into the water, getting into the food we harvest. And we're still connecting the dots there a bit. We know that lots of trash goes out into the water. We know that the sun and waves breaks it down into small pieces. We know that many species of animals eat it. And we also know that bigger animals eat smaller animals. And we also know that we eat those big trophy fish. And so what we're really trying to figure out is how big a vector plastic is for transporting chemicals into the tissues of the animals that we eat every day. That's a big problem, much bigger than big chunks floating out into the ocean.
We don't know exactly what that plastic is. We don't know where exactly it's coming from. And if we're trying to find policy and educational solutions to it, we need to know what we're targeting. We can't just ban plastic. That's not going to work. What kind of plastic is it, and what's the best policy route to reduce it? Is it a ban? Is it a fee? Is it market change? Is it education and behavior change work? What's the best way to tackle it? And until we know exactly what we're dealing with, we're not going to be able to design the right programs to address it.
Yeah, so Chesapeake Bay is one of the most polluted areas because there's a lot of urbanization in that area, and it's in the mid-Atlantic seacoast, so it's highly urbanized all around there. And one thing that kind of glossed over, let me go back for a moment.
I really enjoy it. If you're...
It's not gonna work. Give me a minute. Because the one I was mentioning on the birds, One challenge is caps. Yes, plastic caps. What happens is they float on the ocean, and seabirds see them, and they can distinguish between the cap and an actual fish. So they'll swallow these sea caps, and they'll the little plastic caps, and they'll get stuck.
It was completely legal.
Inside the bird until eventually they fill up the digestive tract, and the bird doesn't have a way of eliminating that. And so it fills their digestive tract, and then they don't get enough nutrition. They literally starve to death because whatever else they eat, they're full, all right? But they're full of plastic inside. It's very challenging. So caps are a problem. Recently,
and as the scientific literature on this issue,
Summer Research Institute, she was drinking some juice, and the cap was made out of recyclable plant material, which was really neat. It looked just like a red plastic cap of a bottle, but it was made out of recycled plant material. So that's biodegradable. And that's the opportunity, you know, the challenge and the opportunity to make good out of these things so that the material is recyclable. Okay, this one is on the microbeads, which is a little different. Because now they're trying to trace this, and the bottom line that it's coming from.
Sick of red, itchy mosquito bites? This genius college student just solved a 210 million year old bug problem.
Giving off these microbeads. Originally, the microbeads were put into gels for washing, for scrubbing.
There's been a lot of attention lately on the tiny additives in our shower products. It seems, without many of us realising, they've been stuffed full of plastics.
Designed to make things a little bit rougher and to get a better clean, but a lot of the products that they're used in go straight down the sink and then out into our lakes and rivers and oceans.
Called microbeads, these tiny plastics have been causing so much alarm that supermarkets are in the process of banning the bead from their shelves. But in the stomachs of our seafood, researchers are mostly finding a different kind of microplastic.
The major thing that we were finding were these fibres, and so that really begged the question, where do they come from?
They're going down our household drains at an astonishing rate, but barely anyone seems to realise.
if animals that we're eating are eating plastic, we could potentially make that assumption that these chemicals are in our seafood.
What kind of microplastics are ending up in our marine life, and how much damage can they actually do? When I decided to take a closer look at microbeads, I didn't realise just how close I was going to have to look.
They're so small, aren't they, these tiny little beads?
Oh, they're tiny. We're getting sizes right the way from 1 millimetre all the way down to several micrometers, if not smaller.
The man helping me filter these rinse-off cosmetics is ecologist Dr. Mark Brown. He's been consumed with the problem of microplastics in the oceans for more than a decade.
It is a huge problem. So if you look at the amount of plastic in the environment, over 85% of that is microplastic.
The problem with microbeads is they're so small you need a filter paper to catch them. They're too small for our water treatment systems, but small enough to be easily ingested.
Over recent years, the amount of research has increased, and we've started to show that they're persistent, bioaccumulative and toxic.
3 years ago in the US, scientists trawling for microplastics in the Great Lakes found concentrations as high as 400,000 particles per square kilometre. They were amazed by how many tiny spherical beads they found in the mix.
It isn't just microbeads, it's much larger bits of plastic breaking down into the same micrometer-sized fragments. And so we're really concerned as to whether or not these particles could be accumulating in humans and wildlife.
The evidence shows they are, even at the very base of the food chain. Zooplankton, for example, are a major source of food for fish, whales and seabirds. These were filmed under a microscope in just one drop of water. Normally, they draw algae towards their mouth by creating currents with their legs. But when tiny fluorescent particles of polystyrene are added to the water, they eat those instead. Microplastic is now regularly being found in wild-caught zooplankton in the North Pacific. Just through eating these tiny crustaceans, salmon are thought to be consuming around 90 particles of plastic a day.
So these particles look so small that if you swallowed them, it doesn't look like they'd do much harm. I mean, don't they just sort of pass right out the other side?
Well, this is what we thought until we started doing experiments whereby we were actually feeding these types of particles to them. We were astounded by actually what we found.
I'm much more disturbed by what Mark shows me next.
So we know that invertebrates, in particular mussels, are exposed to microplastics in the environment. What we really wanted to find out is whether or not these tiny particles of plastic get any further than the stomach itself. So we exposed these mussels to tiny particles of polystyrene, and we then tracked these particles in the tissues of the mussel itself.
This footage, captured by marine scientists at the University of Connecticut, shows how tiny bits of plastic are drawn into the mussel and along the gill filaments. They get trapped here just like food particles and pass down the ventral groove into the mussel's mouth. But no one knew they could penetrate the gut barrier until Mark took samples of the mussel's blood. When the blood is analysed days later under a special infrared microscope, the molecular vibrations of plastic can clearly be identified.
And here you see right in the middle of the actual slide there is the polystyrene bead.
So that means that the plastic has made it from the stomach of the mussel into the circulation?
It has, yes.
That's astonishing. So how long have you seen the particle remain in the circulation?
They've lasted in the actual mussel 4 months. But more disturbingly, as these particles of plastic get smaller, which is what they'll likely do through the breakdown in the environment, the rates of transfer actually increase massively. The concerns that we have really is that it can cause inflammatory responses, so the body of the mussel itself recognises it as a foreign particle and starts attacking that. Because the particle can't go anywhere, you get scar tissue forming around that.
But the reaction to a foreign body in the tissues is just one of the side effects.
What's most concerning researchers is not just the physical damage caused by microplastics when they're ingested, it's the toxic load from the chemicals they carry.
One of those researchers is Dr. Chelsea Rockman from the University of California.
I'm an ecotoxicologist, so I look at the fate and effect of chemicals and plastic debris in our environment. Plastic is kind of like a little sponge for a lot of the chemicals that are already out there, the pesticides, the flame retardants, industrial chemicals, etc. Plastic concentrates, hyper-concentrates these chemicals at very large concentrations, sometimes 1 million times what we find in the water column. So PCBs, which were banned in the early 80s, DDT, which was banned in the early 70s. And I find these on every single piece of plastic I take out of the ocean. Metals like copper, lead, nickel, cadmium.
Plastic also contains unique chemical additives of its own from the manufacturing process, such as flame retardants and antimicrobials.
So the big question there was, do these chemicals associated with plastic debris end up in animals when they eat them? So basically we set up a study in the lab where we fed fish plastic that had these chemicals associated with them. We fed them environmentally relevant levels.
Dr. Rockman exposed Japanese Medaka to plastic particles that had been pre-soaked for 3 months in San Diego Bay. After just 2 months, higher levels of what's known as PBTs, or persistent bioaccumulative and toxic chemicals, were measured in the flesh of the fish, particularly flame retardants unique to the plastic.
So a lot of these chemicals are fat-loving and water-hating. But once they transfer from the water into that fat phase, so the fat in a fish, they're incredibly persistent. I might have, a mechanism in my liver to take that PCB and break it down into a safer form. But once my liver is overtaxed, it might have a hard time doing that, and I'm going to start storing those chemicals in my body.
Chelsea predicted signs of damage would first be seen in the liver. Here she observed cell death and excess fat, a sign of liver overload. One fish even developed a liver tumour.
And when we've taken fish in the lab and fed them the virgin plastic that doesn't have this mixture of things from the environment, we see less of an effect in the fish. So this mixture is having an effect.
Even at very low concentrations, flame retardants are known to cause endocrine disruption, an effect observed in the fish.
Endocrine disruption is a disruption in the hormone system, which is what controls reproduction. So if that's not functioning, some people joke, if you don't reproduce, what are you here for? So it's a very important system.
Dr. Mark Brown also found chemicals transferred from the plastics to lugworms, a common marine sediment dweller.
We saw reductions in survival, reductions in immune function, and we saw a reduction in their ability to feed and process sediment. Things like triclosan, which is sort of an antimicrobial, is added to plastics, and that was one of the major killers of the worms.
Worms that process sediment are crucial for the survival of a complex food web of organisms.
And so when you remove these worms from the environment, you see a complete reduction in the numbers of animals and plants that can actually live on that shoreline.
These studies raise the important question: if chemicals can transfer from plastic to marine life, how much of our seafood is eating plastic?
I got it. It's huge though. Ah! Okay. Well, maybe it's huge. Let's see.
Here in Sydney Harbour, we're out catching some of the state's most popular eating fish.
Oh,
or at least trying to.
Huge. This is called a tiddler. That's not what you're after, is it? Oh. We've looked right the way throughout Sydney Harbour, which is a really big harbour, and we found a surprisingly high concentration of microplastics in the sediments, and up to 60 per 100 mils of sediment. That's a really high concentration.
So is that why you think you'll find plastic in the fish?
Yeah, so because we did find high concentrations in the sediments, the first thing we wanted to do was to see which species it was getting into, if any, and so we targeted the fish that were feeding on the sediment. And this is a mullet. This is really a target fish for us. And these guts in here are full of sediments.
So this is a popular eating fish?
It is popular. It's not quite as tasty as the bream. It depends on your taste. These bream are really tasty, so these are really targeted by the recreational fishers.
We're taking these fish back to the Sydney Institute of Marine Science, where researcher Jen Halstead has been looking through their guts for any traces of plastic. Her studies have revealed that 30% of the mullet and 13% of the bream have plastic in their guts. But typically, it's not coming from face scrubs or shower gels.
So I've just found something that looks suspiciously like a plastic. Do you want to take a look?
Yeah. Doesn't really look like a microbead at all.
Yeah, well actually most of the microplastics that we're finding are in these forms of fibres, so that looks a lot like what we've been finding.
So is that a plastic fibre?
Yeah, well, we actually don't know at this stage. It could be synthetic, it could be natural. That's why we need to take under further investigation.
These results mirror a study 2 years ago by Dr. Chelsea Rockman, who looked inside the guts of fish from both Indonesia and the US.
I'm collecting fish from local fishermen that are selling them for human consumption, either out of a local market, straight off the dock, as you see here, or it's actually going through Pillar Point Fisheries over here, which then gets shipped.
Back in the lab, Chelsea discovered around a quarter of the fish from each country had debris in their guts. But the type of plastic differed.
So what you see back here is a really good example of a piece of plastic taken from a fish in Indonesia. So this is from a silverside, which is a planktivorous fish, actually about this big. And what's a little bit disturbing about this one actually is that people eat the entire fish. And this is an example of where this plastic actually would go to, be transferred to a human.
In Indonesian fish, all of the debris was microplastics from larger, broken down pieces. But in the US, Chelsea mostly found microfibers.
But if you look closely at this, you can see like the actual, nylon intertwine. That does not look natural, plant-like.
Chelsea didn't pinpoint the source of the fibres, but with the help of vibrational spectroscopists at Sydney University, Dr. Mark Brown has followed the trail further.
The forensic techniques that we use shine an infrared beam or laser onto the sample. So we use that absorbance and reflection of light to tell us the type of polymer that we're actually finding there.
The vibrational fingerprints of fibres found in Sydney fish do indeed match plastic, but from a source that to me was totally surprising.
When we match this to a database of polymers, it clearly identifies this one as nylon. The second one here matches to polyester, polymers used in clothing. They seem to have a high fibre diet and it's full of synthetic fibres. They certainly seem to be the same types of fibres, same physical structure, the same colours.
Well, with the mullet, we caught 30% of them had a microplastic particle, at least one, in their gut at the time that they were caught. If you model that, it actually means that pretty much every mullet is eating at least one microplastic particle every 3 or 4 days.
I'm amazed, but Mark has suspected it all along. He's looked at multiple shorelines on 6 different continents, and in each case, fibres were the dominant microplastic.
We expected to find lots of small particles from either from the facial cleansers or from, larger bits of plastic that had broken down. But the major thing that we were finding were these fibres. What was peculiar about what we were actually finding was the proportions actually matched the types of polymers used in the textile industry, not only in terms of the types of fibres, but also in the numbers.
The closer they were to sewage outfalls, the higher the concentration of fibres.
And we found exactly the same types of fibres, acrylic, nylon, polyester, being emitted from your sewage treatment works.
The simple answer seemed to be that fibres were escaping from washing machines.
So most of the fibres that we were finding in the environment were polyester, so we essentially chose some garments that are made out of polyester, things like fleeces, which are the poster child for sustainability because a lot of bottles get recycled into them. And we essentially put those into washing machines separately, and we counted the number of fibres that were coming off.
You probably haven't thought that much about the proportion of clothes we wear that are plastic. But today, around 2/3 of the clothes we buy are made of synthetic fibres.
The so-called eco-fleece sheds almost 2,000 plastic fibres each wash. Other polyester garments aren't much better.
They release similar quantities into the environment. It doesn't seem just to be one type of garment, they all seem to be doing it.
But can these thin fibres carry the same chemical load as the other more spherical plastics tested?
I think the toxicity of the microplastic particles will vary with their shape and size. So the fibres have an incredible amount of surface area. The more surface area, the more likely they are to actually carry those other contaminants, and they would then be transferring into the fish tissue.
Aside from the direct effects of eating plastic, chemical doses are already known to biomagnify up the food chain.
These chemicals might absorb to the plankton at the bottom of the food chain, and one fish eats 10 of those plankton. Now that fish has a larger dose, right? 10 times the dose of the plankton. And then several of those are eaten by a larger fish. And so the question is, how is plastic contributing to this thing where we're seeing these large concentrations of chemicals in top predators?
One of those top predators is us. And it's well established that toxic chemicals can transfer from contaminated fish to humans with serious side effects. With all the billions of people wearing plastic clothes, suddenly the problem appears a lot more diabolical than microbeads.
We've been speaking to the public, government and industry. The public have voted this one of the most important issues to be sort of tackling. We've spoken to the government about it, yet they seem to be focusing on other activities, things like microbeads and also packaging. When we have gone to talk to clothing companies or appliance manufacturers for washing machines, the appliance industry and the clothing industry haven't been helpful.
Mark says a simple filter could be added to washing machines to stop all kinds of toxic fibres from reaching our seafood. And do we really need all the industrial chemicals added to our clothes and other plastics?
We're seeing all sorts of chemicals come on the market, up to about 15,000 per day. The problem is that we're not doing the tests to keep up with the types of impacts that could be occurring. Which one's causing the impact and which one's is causing more of a worse impact? If we understand that, we can start making choices.
We need a healthy ocean because it is all connected, and our fate.
So who would have known that clothing is actually contributing to all of these microfibers getting into the food chain and the food web. And like the doctor said there, the researcher, it's hard to get industry to pay attention to this because of a market economy, right? So it has to be the solution also has to be cost effective. Otherwise, industry is just not gonna look at it. Okay, let's see where we're at. It's 12 o'clock. I want to, since he mentioned industry, I want to show now a little video here that was done a couple of years ago. And this one is from the Wall Street Journal. And it is an interview that was done with two industrial giants who have partnered. That is Tyson Food Company and Waste Management, right? Which Waste Management is involved in recycling, and Tyson, of course, makes all these food products, including the famous hot dogs and all that. So this little interview is with the Wall Street Journal. The lady is representing the journal, and the man in the middle here is from Tyson, and then the one on our right is from Waste Management. And they're going to explain what they've done on the streamline of production. So I found that this is the type of creative thing that we need to encourage, so that the industry will take responsibility on the garbage that we're producing.
Because everything great is birthed through discomfort.
Real empathy says, I see you, I feel you, I hear you. That's what truly matters.
A little advertisement.
In the chicken business, what do you do with all the chickens, and what do you do with all that's left over, and how is this actually being profitable for both of you?
Okay, so I don't want the storyline here to be, though, that Tyson has great trash. Okay, we're going to do better than that. But if you look at our business, we bring in two types of raw materials. First, the animals, the cattle, the hogs, and the chickens, which we process, or the other non-protein items, and then we bring in the raw materials we need to process those, right? So on the animal side, we're incredibly efficient. All we lose is the cluck, the moo, and the oink, right? And so we create value streams for all of the parts of the animal. Some go into animal food, some would go into pet food, some go into renewable fuels, those type things. So if you look at that stream, we're incredibly efficient. If you look at the other raw material stream, then that's the stream that generally creates some waste. And that's where great partners partners like Waste Management come in. And what David and his group have done with us is both support and challenge us to be as efficient as we can and to try to create as many value streams as we can. For example, let's take our pork division. It's kind of the freshest on my mind. We began with one of our pork plants to work through what we were doing to create waste that could not be valued up, right? So it may be organic contaminants on corrugated material and that type of thing. So they worked with us on programs.
Can I just interrupt? Can you explain that? I mean, you cannot recycle, apparently, corrugated cardboard if there's oil on it.
Right, because that's generally going to get sent back into the corrugated plants, which are then going to make packaging materials out of it. So we have to keep the streams separate and clean. So they worked with us on a program where we could train our team members, the value of those waste streams, but then efficient processes to separate the plastics, the wood, the corrugated materials, and that type of thing. And so kind of fast forwarding where we are today in our pork plants, about 70% of our waste stream is now recyclable. So very efficient, and it's been a great success story for us.
And you know, and it really brings home the point, right? Which is, you know, when Donnie said it, what he's doing is lowering that conversion cost, right? I mean, we can't do anything about what we can sell that cardboard for, let's use, or plastic or metal on the back end. Those are markets that, you know, we don't set the prices on. But what we can do is affect those conversion costs up front. So if we can lower the conversion costs now, even if the cardboard value comes down, it's still profitable to recycle. They can still save money doing it. And so that's what they've done. They've trained their folks to lower the processing costs, right? And that is what's going on. That's why I say you can't think of recycling as a homogeneous whole, because a business like Tyson has every incentive to do that because they can save money.
You are actually making a profit on recycling at the moment.
Yeah, we cover the cost, not by much, but we make some profit on what we recycle. Yes.
And that's after taking into account even the 30% that you can't recycle.
Right.
Okay. All right.
And so you know, but when you look at residential recycling, different animal, right? I mean, that's what we've done in the last 10 years is we've tried to drive recycling rates up by doing what we call single stream recycling, put everything into one bin, right? Remember, when recycling first started, it was sort of done the way Tyson did it, which is we asked the consumer to separate it, and that drove down the conversion costs. We could do it profitably, but the problem was it was difficult for the consumer, and so you couldn't get as many consumers to do it. So we then moved to single stream recycling, mix all the components together, and we'll recycle it. We haven't done a very good job of educating the consumer as to what can be put into those bins. So the recycling rate goes up, but the contamination of the material, that cardboard with oil on it, goes up also because people put the wrong things in those containers. What does that do? Drives up the processing cost, the value on the back end goes down, and all of a sudden that's how recycling becomes unprofitable.
Single stream recycling bin, how much of what's in there should not be in there?
Well, you know, it depends on what city you're in. But we have contamination
smarter and less smarter recycling cities?
Oh, absolutely.
Yeah.
Absolutely. We have contamination rates anywhere from 20% to 50%.
Wow.
I mean, when you have 50% contamination in recyclable materials, that's garbage.
Okay, so a lot comes down to human behavior, right? That's really the challenge. The human behavior. So even if we have recycling, but we're recycling contaminated material, then that defeats the purpose because it contaminates the whole bin. One box that is dirty will contaminate the whole bin. So it is challenging, and it's modifying the behavior. A follow-up on that, on the single stream, because I still remember, again, I'm ancient enough to remember when we used to separate the recycling things. I don't know if any of you remember that, but we used to put, for example, newspapers went in one bin, and glass bottles, glass jars went into another bin, and then plastic and wood and so forth. So there were all these different bins, and what do you keep that at home? Taking space, it was difficult, awkward. At times you even had to haul it out on different days, okay? So Monday was plastic day, and Wednesday was newspaper day. It was getting too cumbersome for the lifestyle of the consumer, okay, of people. And that's when they came up with this idea of single stream. A single stream, we take it for granted, but it was, like the man said, from waste management, now the industry is taking the hit of that single stream because they have to do selecting of the material at some point and reclassify it.
We all have an opportunity.
Put back the sound. We're all familiar with these scenarios.
To contribute to a growing recycling success story by recycling often and recycling right. This helps preserve valuable landfill space and saving precious natural resources like trees and energy. Forward-thinking companies like Waste Management are introducing and expanding single-stream recycling programs for both residential and commercial customers. Non-recyclable contamination slows down the recycling process, increases the cost of recycling, and decreases the value of the end product, and that's bad news for everyone. So to recycle right, whether using a cart or bin, do not place the following in your recycle container: plastic bags of any kind, including grocery and dry cleaning bags, and do not place your recyclables in plastic bags, polystyrene and foam containers, food or yard waste, hoses, extension cords, and hangers. Electronic waste, including cell phones, computer parts, batteries, and small appliances. Automotive parts, such as disc pads, tire rims, and car batteries. Motor oil, paint, hazardous chemicals, or propane tanks. Food-soiled cardboard, hot and cold beverage cups, paper plates, towels, and tissues. Dishes, cooking utensils, pots and pans, coffee mugs, or ceramic pots. And no liquids of any kind. And please do not use your recycle container for extra garbage space.
Remember, it's easy to recycle right, especially with single-stream recycling, where all recyclables go into one cart or bin. No separating required.
Here's what you can recycle. Paper, including newspapers, junk mail, magazines, office paper, and phone books. Paper board, such as cereal, pasta, and tissue boxes. And cardboard that fits into your container. Plastic bottles and containers, including water and drink bottles, milk jugs, detergent, and shampoo bottles. Remember to empty and rinse, please. Aluminum cans and steel and tin cans, and glass bottles and jars. Please note that recycling guidelines vary by community. Check your local recycling guidelines for specific details. Companies like Waste Management are working in partnership with counties, cities, businesses, and communities in our area to make recycling easier and more cost-effective. And each of us can step up too to make it happen. Together, let's all recycle often and recycle right.
Okay, so you see the challenge is there's no separation, but there is separation. Okay, we don't have to separate the items into the various components that we had to do earlier, but still there are many things that cannot be recycled. Significantly, in my mind, for example, is the plastic bags. There are plastic bags all over the place. Now I understand that those plastic bags are actually being made biodegradable, but still they cannot go into the recycle bin, all right? So it takes that consciousness to know what is recyclable and what is not recyclable. All right, shifting gears a little bit back into the environment, how creativity, here we have to really stimulate creativity to make, as they say, lemonade out of lemons, all right? What do you do with contaminated water sources, especially in high urban areas? So this is a creative idea from a couple of guys that wanted to do something, again, Baltimore Harbor and Chesapeake Bay, that area that has high density of several cities and states around it, dumping into the bay, into the mid-Atlantic. And so they built this machine, this contraption, that looks, I don't know, like a giant beetle or something. And you can see that it's run by solar panels, but that's only used under the natural, the way it's called the Baltimore water wheel, all right? And it's the actual flow of the river that makes this wheel collect trash. You'll see how it works.
I think there's a little bit of apprehension involved in trying new technologies, and a lot of people heard the idea and said, that's pretty off the wall. I don't know if that'll ever work. I used to walk across this bridge every day, and I would see the trash coming down the river, and I'd hear the tourists say, "Oh, this harbor's disgusting." So I thought about it every day on my way to work, and this is the idea I came up with. And my partner Daniel and I enlisted his help to help put it together and put it in on May 8th.
So here we are on the Jones Falls in Baltimore's Inner Harbor on a rainy day, standing on the water wheel, and which is behind me here. You can see this is the water wheel. It's being turned by the current of the Jones Falls, which is flowing very rapidly because we just had a pretty large rainstorm. And that wheel is turning this conveyor belt that is picking up all of this trash that is flowing down the Jones Falls. You can see we've got a lot of plastic bottles.
People all want clean water. They all want the ability to swim or recreate in water without coming into contact with trash or sewage or stormwater pollution. And you can see a lot of that, especially online. There's a lot of concepts out there for cleaning up trash in the ocean. And just those concepts become very, very popular on the internet. And part of the power of the water wheel is that it's here, it exists. People can actually see it operating every day and cleaning up the trash. John is a huge inspiration to, I think, a lot of people. Here's a guy who solved this problem of just trash in the waterway, something that, thousands of us have been looking at for a very long time. And, he actually had the ability to think about the problem and come up with this brilliant device.
As you can see, it moves kind of slowly, but slow and steady in this case is just fine.
We've captured over 3 million cigarette butts with the water wheel since we installed it. Second to that, I would say plastic bottles. We've probably captured about 50,000 plastic bottles since we installed it. And then styrofoam, basically anything that floats. It's completely sustainable in that it's powered by hydropower, and when there isn't enough current in the Jones Falls, we have solar panels, which provide solar power to pumps that actually pump water onto the water wheel to keep it turning, even when there's not enough current.
Okay, so just let me stop for a moment because I thought that the mechanics were interesting. It's a passive system and it's self-sustained. So it's mostly the flow of the river, the flow of the water that makes the wheel turn. And as the wheel turns, it has a conveyor belt that picks up the trash that has been accumulated by the boom. We haven't talked much about that boom, but that boom is basic for collecting the trash, concentrating it to a particular corner. And there, the conveyor belt then picks it up and dumps it into a bin. Now that bin has to be taken to a trash disposal area, but at least it has concentrated it. And what I want to mention is that this concept of the boom is also being used by the other team that is cleaning up the garbage patch, the Great Pacific garbage patch in the Gyre. And so essentially what it does is it generates like an artificial shoreline. It's an artificial shoreline where trash accumulates. And then when there's not enough flow in the river, because the river, the current will vary according to rainfall or not, right? Then when there's not enough flow, the solar panels take over to move the conveyor belt.
So I'm going to go ahead and turn it on. Make her go. The water's being pumped in 2 stages from the harbor up into this reservoir, and then from the reservoir up into the wheel. And so that's what's making the wheel go around today, because the river, we've had a dry spell and there's not much flow coming out of the river. Even on these dry days, we still get a fair amount of trash. It's like, a couple trash cans full, but after a storm, we'll get as much as a couple dumpsters full. So the power from the wheel, the turning wheel, is transferred to the conveyor and to the rake system through a system of gears chains, belts, pulleys, so it doesn't really care if there's a big 2,000-pound log on it or just a load of styrofoam. It just keeps on turning.
So here we are once again at the back of the water wheel, seeing what kind of trash is coming over the conveyor belt today.
I love hearing people talk on their cell phones and just be like, you wouldn't believe what they have here in Baltimore. You know, it's called a water wheel and it's like solar powered. And so hearing that excitement from everyone has just been terrific. Ultimately though, our goal is to actually put the water wheel out of business. We know that it's an end of pipe solution. It's great because it's immediate and it's innovative, but the real solution is that people need to change their behavior.
We've heard lots and lots of people say, oh, the harbor will never be clean. You can never get all the trash out of the harbor. I think, you know, we're not taking all the trash out of the harbor, but we've made one big dent, a noticeable dent that's noticed by everybody who uses the harbor, who boats on the harbor, who lives on the harbor, who jogs the promenade. We had one article that this is the most promising technology for keeping the plastic trash out of the oceans. And, you know, we're hoping just to clean up this harbor right now. But I think we could take it to a bunch of different places and make it a valuable technology or a valuable asset to keeping the oceans clean, the rivers clean, the harbors clean. It's a dirty job, but it's a worthwhile project.
Okay. Now that same concept of the boom is being used by this other, the ocean cleanup, but those are floating booms. So I wanted to, let's see how we're doing with time. 10 minutes. We may not have time to look at them. That same concept of the boom is being used by the ocean cleanup with a boom that floats through the ocean and is driven by the currents and the wind at different rates to also concentrate the trash. So it's the same basic concept of essentially generating an artificial shoreline to concentrate the trash so that it can be picked up and taken to a dump. I want to shift a little bit to the land now and show you some bioremediation that is being done on the shore. This is after the oil spill of remember that platform in the Gulf of Mexico, the Deep Horizon, that caught on fire and it was
we could let this crispy, juicy
to the Gulf of Mexico. So it's looking at the ecology of the Gulf, particularly
tender chicken speak for itself. But then, who would speak for the crinkle-cut pickles? Introducing McDonald's new crispy chicken sandwich.
The species we study is called smooth cord grass, and it's the foundation.
Sorry. So again, this is the shoreline of the Gulf of Mexico, and they're looking at this cord grass, which is similar to our mangrove on this side of the East Coast to stabilize the coastline.
Species along the coast of the northern Gulf of Mexico and along the Atlantic coast. This species is incredibly important for building land and keeping land from falling into the sea. We went out to several sites that received heavy oiling after the spill. We found that the bacterial community inside the tissues of plants shifted to incorporate more bacteria that are important for breaking down oil. This is also really important because our collaborators have found that there's also oil inside of the plant tissues that still needs to be broken down. So it's possible that these bacterial shifts are going to be important for continuing to clean up the oil spill inside of the plant.
This is Bay Jimmy. It was one of the worst impacted areas after the Deepwater Horizon spill, and we used the shoreline to test different strategies for remediating the oil, for removing it from the surface. And after remediation, I went in and planted Spartina along the shoreline in different plots to compare what rates of erosion were like using different planted varieties versus leaving them unplanted after remediation. This stake right here is the back of a plot that we set up in 2011 where we were comparing planting versus not planting, and the plot extended 15 feet towards the water, and then in front of the plot was an additional 15 feet, and all of that's gone now. So since 2011 we have 30 feet of erosion up until this stake. The aspect of Spartina alterniflora is it's a very powerful ecosystem engineer, which means that it physically impacts this entire ecosystem. So just the presence of the marsh here is dependent on the ability of Spartina to hold the substrate in place.
Well, the elegance of focusing on Spartina is that whether we're here in the Gulf or on the Atlantic or on the Pacific, there are Spartina everywhere. Some Spartina have been artificially introduced and have proven to be problematic, but the native Spartina and other congeners and related species that serve a similar function, that effectively engineer coastlines, can serve a similar purpose.
So now we're taking a closer look at these bacterial communities living symbiotically inside of root tissue to see if we can identify which bacteria are the best at biodegrading oil inside of plant tissue. And what we'd like to do is identify the best bacteria that we can use to inoculate plants in the future that are going to be used for restoration purposes. So instead of just putting a plant out there, we're going to put out a plant-bacterial combination. And that combination of organisms is going to help clean up oil faster.
Okay, so two basic concepts here that I want to emphasize. One is recycling and cleaning and taking out garbage from either land or ocean out in nature, right? So then the other one further, after we take out whatever garbage is there, we still have an area that needs to be restored to its original environment, and then that is bioremediation, which is going beyond taking out the garbage, the trash that has contaminated an area. It's the bioremediation is to try to bring it back to its original state. And nature actually has a way of doing that because nature is overabundant, all right? And many times if we leave an area alone, it will restore itself. Sometimes it needs some help if the damage has been too drastic. 5 minutes here, there's one last one. Let's see if I can pull this up for a moment because it's beyond. One last video, I want to show it because it's something positive that is being done in China, which is regrowing a desert.
Little, if any, rain and scorch.
Yeah. In the Mongolian region, central China, there's a huge area that had become a desert because cattle essentially wiped out the vegetation there, and now they have a project of reforestation.
Scorching temperatures, not exactly ideal conditions to support vegetation. But turning that logic on its head is this desert in North China's Inner Mongolia Autonomous Region.
According to our calculation, there are over 70 kinds of crops growing here. Many are not planted by us, but they just grow themselves.
Crops like corn, tomatoes, sorghum, and sunflowers, transforming more than 200 hectares of sand dunes into an oasis, all within 6 months. It's all thanks to new technology developed by researchers at Chongqing Jiatong University. They developed a paste made of a substance found naturally in plant cell walls, When it's added to sand, it's able to retain water, nutrients, and air.
The costs of artificial materials and machines for transforming sand into soil is lower compared with controlled environmental agriculture and reclamation.
The research team has big future plans. This fall, it hopes to transform an additional 200 hectares of desert and possibly more than 13,000 in the next few years. The method could be promising for China. In 3 years, the country hopes to reforest 50% of degraded desert land that can be treated. By 2030, the United Nations is aiming to reach zero growth of desert farmland around the world. So China's breakthrough experiment in converting sand to soil is promising for making land seemingly hostile to life fertile ground. Frances Coe, CGTN.
Okay, so that's another example. Basically, it's a little fast, but it uses a paste that is made up of plant material that is inserted into the sand and hydrated. And then that paste is able to retain much more water than the sandy soil, because you know sandy soil drains through. We have a lot of sandy soil here at St. Thomas University because we're actually sitting on top of a sandy ridge. And when we get these rainstorms, it drains right through and the water never accumulates. But inserting this paste, plant material paste, then that paste holds onto water, hydrates, and holds it long enough to have the plant, the living plants grow there. As more living plants grow, then more humidity accumulates in the area. And it's kind of a synergistic effect. Those plants also, as they grow, eventually the leaves will fall off and rot and accumulate more plant material mixed in with the soil with a sand that's called detritus. And it is essentially turning a desert into either a forest or a farmland. And that's the goal there. So this is an experimental station. They've shown that it works, and now it can be scaled up. All right, I'm gonna stop there. And maybe one or two more videos here that you can look on your own on the PowerPoint. But I'm gonna stop there because it's 12:30 now. Questions, comments? The basic idea here is to put creativity to work, asking the Holy Spirit to inspire us and see what we can come up with that will help nature. First, getting rid of the trash, minimizing the trash that we're polluting, and then recycling that into something that's usable. The three little words that are always the buzzwords for recycling here is reduce, reuse, and recycle, right? So reduce means trying to use less stuff, all right? We don't need to have that much clothing. We don't need to have that many shoes or buy that much plastic. Notice how everything comes packaged in plastic, right? Sometimes 2-3 layers of packaging before we get to the actual product. So reduce the amount of stuff really that we're buying and stuff. We may not need all that. Reuse, so single-use material is a big problem. Reuse as much as possible. And then once it's no longer usable, then recycle it in the proper way, in the proper container, so that the whatever recycling company is involved can take care of that. Okay, just kind of scratching the surface by presenting you with some problems and some solutions, and very especially asking the Holy Spirit to inspire us so that we can cut down on the amount of pollution that we're doing on the earth. Thank you once again. If there are no questions or comments, I'm going to stop here and we'll pick it up next time. Okay. Thanks again.
Thank you, Professor.
God bless. Bye-bye.
Thank you, Professor.
Thank you, Professor.
Thank you. Bye.